Hey everyone, this is my Physics 2212 Lab 5 all about magnetic braking. This lab is all about magnets and changing flux. The purpose of this lab is to demonstrate how nature abhors a change in flux and will create its own magnetic field to resist this change. This is explained by Faraday's law, which shows how nature creates its own magnetic field. As a quick preview of the results, it was observed that dropping a magnet down a tube of aluminum foil does in fact make it fall slower. Actually quite a lot slower. The computational model predicted that it would fall in 1.84 seconds, but it actually fell in 2.09 seconds. This experiment all has to do with Faraday's law. Essentially, as I said before, nature wants to resist a change in magnetic flux. Because of this, an induced electromotive force is created in the coils, and this drives a current. This current in the coils creates its own magnetic field to resist the change from the moving magnet. In this experiment, the falling magnet is slowed down by this resistive magnetic field. The system of this experiment was a magnet, and the surroundings was everything else. The mass of the magnet was 0.015 kilograms, the length of the foil was 0.3 meters, the width was 0.06 meters, and the inner radius was 0.024 meters. This experiment was very simple. First, I measured the time the magnet took to fall the length of the aluminum foil normally. Then, I measured the time the magnet took to fall through the aluminum foil. I repeated this a couple of times to get a good data set, and I averaged them. So here's my code. Most of this code was given to me. I just had to change a few things. As you can see at the bottom, I put my aluminum foil's dimensions in the code right here. In this part of the code, I put the mass of my magnet in right here, and I didn't really change much else. In this part, I defined a dipole right here, and I also defined flux, so it could be calculated in the rest of the code. And here's the calculation loop, all of this, as well as this little top bit on this slide as part of the loop. Finally, the force and velocity is calculated right here, and then it is graphed. And that's all that it is for the code. So here you can see the graph is created as well as the elapsed time generated from the code. So here's the elapsed time, and this is the graph. All right, and for the discussion, so for the similarities and differences, both the code and real life showed that a magnet will fall slower through aluminum foil. However, the magnet fell more quickly through the foil in the code than in real life. This could have been caused by a source of error, such as unaccounted friction against the size of the tube, which would slow it down in real life, but it wasn't accounted for in the code. It is also possible I estimated the mass wrong of the magnet, because I didn't actually weigh it. I was just given the mass, and this could have been incorrect, and this would have threw the calculations in the code off. And the other source of error is if I measured time inaccurately, because I recorded a video and I just try to estimate the time based off the video for how long it took. So for the what if questions, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? The induced current would be greater, and this would generate a greater magnetic braking force, so it would fall slower. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The current would be smaller, so there would be less magnetic braking force again, or there would be less magnetic braking force, so it would fall faster. All right, and the conclusions. As we can see in both the code and the experiment, the magnet fell slower through the aluminum foil. This is because of Faraday's law, which explains how nature abhors a change of flux and creates its own induced current and magnetic field to slow the magnet while falling. Thank you for watching, and I look forward to reading your responses. Have a good one.